Okay, so hello everyone. In this video, we will cover paging concept in non-contiguous memory allocation. This video is one part of paging in which we will first discuss about what is paging and need of paging. Then we will solve complex questions related to this, and at last we will see entries in paging table. This concept is very important as it is asked in GATE, UGC NET and many competitive exams many times. So without wasting the time, let's start with the topic of non-contiguous memory allocation. Now in non-contiguous memory allocation, we are allocating memory to different processes in a non-consecutive manner. This is the fundamentally different from contiguous memory allocation, where a process must be placed at as one complete unit in a continuous block of memory. In non-continuous memory allocation, a process can be divided and its part can be placed in different locations throughout the RAM. This is the key concept that makes this approach so powerful and flexible. Suppose we have main memory with 3 available holes of 2 KB, 2 KB and 2 KB each. Now if a process P1 arrives with size of 6 KB, let's see what happens in both allocation schemes. In contiguous memory allocation, we cannot accommodate this 6 KB process because we don't have a single continuous block of 6 KB available. The fundamental rule in contiguous allocation is that if one process arrives, it must fit completely in one location. We cannot divide the process and place it in the different location. This leads to what we call external fragmentation. We have enough total free space, but it's not continuous, so we cannot use it. However, in non-continuous memory allocation, we can solve this problem. We can divide this 6 KB process into 3 partitions of 2 KB each. Then we place the first partition in the first 2 KB hole, the second partition in 2 KB hole and the third partition in 2 KB hole. This way we can successfully allocate memory to the entire process without any wastage. The primary motivation behind non-contiguous allocation is to eliminate external fragmentation. External fragmentation is a significant problem in contiguous allocation because as process arrive and leave, we end up with many small holes that cannot be used for larger processes. But here is the important point. There is a cost to this flexibility. When a process arrives in memory and want to be accommodated, we need to perform division at the exact moment. We need to analyze how many holes are empty, what are their sizes, and then divide incoming process according to available hole sizes. The problem with this approach is that these holes are created dynamically at runtime. Their sizes and number keep changing constantly as process arrive and leave the system. Every time a process arrives and wants memory, we need to analyze the current state of memory. How many holes are there, what are their sizes, and how should we divide the incoming processes. This overhead can become significant, especially in system with frequent process arrival and departures. Now the paging solution. This is where paging comes to our rescue. Paging follows the same basic principle as non-contiguous allocation. We divide process and place them into different location. But the key difference is when we perform this division, instead of dividing the process when it arrives in main memory, which is expensive, we divide the process beforehand while it's still in the secondary storage. This pre-division approach eliminates the runtime overhead. Now here's how paging works. When we load a process into secondary memory, we immediately divide it into fixed size blocks called pages. Each page is the same size, which makes management much simpler. Similarly, we pre-divide the main memory into fixed size blocks called frames, and here comes the most important rule in paging. The page size must always equal to frame size. Each page needs to fit perfectly into a frame. If page size and frame size are different, we will either waste space if frame is larger or won't be able to fit the page if frame is smaller. By keeping them equal, we ensure optimal memory utilization and perfect fit. When a process needs memory allocation, instead of performing complex analysis and division, we simply take its pre-created pages and allocate them to available frames. This allocation can be completely non-contiguous. Pages can be scattered across different frames anywhere in the memory. The beauty of this approach is that we have moved the expensive division operation from runtime when process needs memory to load time when process is initially loaded into secondary storage. This dramatically reduces the memory allocation overhead. Now let's work through a comprehensive example of understanding how paging works in practice. Suppose we have a main memory of 8 KB and we decide to set our frame size to 1 KB. This means our main memory will be divided into 8 frames, which we can number 0 to 7. So we have frames 0, 1, 2, 3, 4, 5, 6 and 7. Each frame can hold exactly 1 KB of data. Now let's say we have 4 processes arriving P1, P2, P3, P4, each with size of 2 KB. Since our page size is equal to frame size 1 KB, each 2 KB process will be divided into exactly 2 pages of 1 KB each. So P1 gets divided into 2 pages, P2 into 2 pages, P3 into 2 pages and P4 into 2 pages. This division happens in secondary storage before these processes even think about entering the main memory. Initially, when all frames are empty, we can allocate memory as follows. P1 first page goes to frame 0, P1 second page goes to frame 1, P2's first page to frame 2, P2 second page to frame 3, P3's first page to frame 4, P3's second page goes to frame 5, P4's first page goes to frame 6, P4's second page goes to frame 7. Now you might notice that in this case we placed pages contiguously. This happens because frames were available in continuous manner. But remember, paging allows non-contiguous placement. If frames weren't available, we couldn't have scattered the pages anywhere. The real power of paging becomes apparent when process start terminating. Let's say P2 and P4 complete their execution and leave the memory. Now frame 2, 3, 6 and 7 become available. We have a total of 4 KB of free space, but it's not contiguous. Suppose a new process P5 arrives with a size of 4 KB. In contiguous allocation, we couldn't accommodate P5 because we don't have 4 KB of continuous space. But with paging, there is no problem at all. P5 get divided into 4 pages of 1 KB each. Since that's our page size, we can then allocate these pages as follows. P5 first page goes to frame 2, P5 second page goes to frame 3, P5's third page goes to frame 6, P5's fourth page goes to frame 7. Perfect. We have completely eliminated external fragmentation. The process doesn't care that its pages are not contiguous. The paging system handles all the complexity. Now, the address translation challenge. Now we come to crucial challenge that paging introduced. The CPU doesn't know about our clever paging scheme. When the CPU execute process P1 and needs to access byte number 3 of process, it simply generates a request for byte number 3 of P1. But where is byte number 3 of P1 actually located in physical memory? Remember, we have scattered P1's pages across different frames. Byte 3 might be in frame 0 or frame 1 or somewhere else entirely, depending on how we divide the process into the pages. This is where we need a mapping mechanism, something that can translate the CPU request into the actual physical location in memory. This translation is performed by hardware component called Memory Management Unit, MMU. The MMU takes the logical address generated by the CPU and convert it into the corresponding physical address in main memory. To perform this translation, the MMU uses data structure called page tables. Now, page tables and address translation. Every process has its own page table. The page table acts like a directory that tells us where each page of process is located in physical memory. The number of entries in a page table equals to the number of pages in the process. Now, let's continue with our example. P1's example. P1 has 2 pages, so its page table will have 2 entries. Entry 0, page 0 in frame 0. Entry 1, page 1 is in the frame 1. So when the CPU generates a logical address, this address is structured in a specific way. It consists of 2 parts, page number and page offset. Let's understand this with a specific numbers. Suppose CPU requests byte number 3 of process P1. We need to figure out which page these bytes belong to and which position within that page. Since each page is 1 KB, which can hold bytes number 0 and 1, we can determine page 0 contains byte number 0 and 1, page 1 contains byte number 2 and 3. So byte 3 belongs to page 1. It's the second byte, offset number 1 within that page. In binary representation, if we need to represent address 3 and we have 2 pages total, we need 1 bit to represent the page number 0 or 1 bit to represent the offset within the page 0 or 1. So address 3 becomes page number 1, offset number 1. In binary, it is 1 1. Now the MMU looks up page number 1 in P1's page table and finds that page 1 is stored in frame 1. Then it accessed offset 1 within frame 1 to get the actual data. Let me give you a better example. Suppose page 0 of P1 is actually stored in frame 2 and page 1 of P1 is stored in frame 4 due to non-contiguous allocation. Now when CPU requests byte number 3, byte 3 belongs to page 1, offset 1. Page 1 is in the frame 4. From page table lookup, frame 4 contains byte 8 to 9. Since frame 0, 1, 2, 3 contains byte 0, 1, 2, 3, 4, 5, 6, 7 respectively, offset 1 within frame 4 means byte 9. So logical address 3 maps to physical address 9. This is the kind of translation the MMU performs constantly. So that was a simple example of this concept. Now moving forward to page table entries. While we have focused on frame numbers as the main content of page table entries, real page table entries contain several details, additional fields that serve important purposes. Let me explain each of these fields and why they are necessary. First is frame number. This is the mandatory field we have been discussing. It tells us which frame contains the page. Without this, the address translation would be impossible. Now the next is valid or invalid bit. This bit indicates whether the page is currently present in main memory or not. Why would a page not be present? This relates to virtual memory concept. Since main memory is limited, the operating system sometimes moves pages to secondary storage to make room for other pages. when the CPU tries to access a page that's been swapped out, this bit will be 0, invalid. We will call it page fault. The operating system then need to bring the page back from secondary storage before the access can proceed. Now next field is protection bits. These bits specify what operations are allowed on this page. Typically we have three permission types: read, write and execute, R, W and X. Read, can we read data from this page? Write, can we modify data in this page? X means can we execute instruction from this page. Now the next field is reference bit. This bit is used by page replacement algorithm. It is like set to 1 whenever the page is accessed, read or written. Page replacement algorithm like least recently used, LRU, using this information to decide which pages to swap out then memory is full. Now next field is dirty bit, modified bit. This bit indicates whether the page has been modified since it was loaded into memory. When a page is first loaded, this bit is 0. If the CPU write to the page, this bit is set to 1. The information is crucial when the page need to be swapped out. If the dirty bit is 0, we don't need to write the page back to the secondary storage. Since it has changed, the dirty bit is 1. We must write the updated page back to maintain data consistency. Now the next field is caching bit. This bit determines whether the page should be cached in faster memory like CPU cache. For data that's accessed frequently and doesn't change often, caching improves performance significantly. So that's it for this video. We will meet in next video. Until then, bye bye.